All right, so we've tackled multiplication and division of rational expressions. The great part about them is that the fractions just come as they are. Remember, we don't need common denominators for multiplication and division problems. We didn't need them for fraction multiplication. We don't need them for rational expression multiplication. But when it comes to adding and subtracting, the game changes. We do, before we add or subtract two rational expressions, because it's the same for fractions, need those to be expressed with a common denominator. So in this problem, we're going to subtract y over y minus 2 minus 8y minus 8 over y squared minus 4. A pair of fractions, we want to subtract the latter from the former. So, just as in our last example where we multiplied, I want to start by identifying all the factors that I can identify. So I'll factor all four of these parts, the numerator and denominator of the first fraction, which there's really nothing I can do to factor there. It's just a y and a y minus 2. But the numerator and denominator of the second fraction do factor in meaningful ways. 8y minus 8, we can pull out the greatest common factor of 8 with a cofactor y minus 1. And y squared minus 4, we can factor again using the sum and difference of the perfect squares. Y plus 2, y minus 2. Now, what do you observe when you look at the denominators of these two fractions? What jumps out at you off the page? They both have a y minus 2 in common. So when it comes time to think about a common denominator for these two fractions, we can use that observation. And what we can do then is look at these two denominators and say, if I want to put these two fractions on the same footing, denominator-wise, I don't need to introduce any new y minus 2's. I already have all the y minus 2's that I need. What the first fraction lacks that the second factor has is what? Y plus 2. So the idea is that we're going to use y plus 2 times y minus 2 as our common denominator. The second fraction already has that as its denominator, and so we're not going to have to change it at all. We just need to change the first fraction so that its old denominator, y minus 2, becomes the new denominator, y plus 2, y minus 2. So how do I change this fraction so that its denominator now has a y plus 2 downstairs? Whoa. So if I want a y plus 2 in the denominator of my first fraction, what do I have to do to the numerator?
Same thing.
Same thing. Multiply it by y plus 2. Oh, there we go again. Great. So multiply the top by y plus 2 as well. And remembering that multiplying fractions is the same as just multiplying across, we can just think of this now as a single fraction. Y plus 2 times y on top, y plus 2 times y minus 2 on the bottom. And now both of my fractions have the same denominator. And now that I have two fractions with the same denominator, how do I subtract them? What's my new denominator going to be? Downstairs. Just as an analogy, let's think about the problem of subtracting 5/16 minus 3/16. The denominators are the same. So when I subtract these two, what's my denominator? 16. The denominator remains the same. What's the numerator? Yeah, that's where the subtraction happens, right? So the subtraction happens in the numerators. The denominators remain the same. Same principle. If we were doing this fraction problem, we would then also have a simplify step at the end, right? 2 over 16, we could simplify into 1 over 8 by dividing top and bottom by 2. So that's the inspiration behind what comes next. We keep the denominator exactly the same. Y plus 2, y minus 2. That's my common denominator. And in the numerator, we have a subtraction problem. We're going to subtract y plus 2 times y minus 8 times y. That should say y minus 1. Great. So now we have a single fraction. That's big news. That means we've gotten over the hump in this problem. We've navigated the common denominator correctly, and we've subtracted in the numerators as we meant to. And now is actually the only part in the process of doing fraction arithmetic where I'm going to recommend that we try and multiply things back out. Because we won't know whether this big ugly fraction can be simplified until we can identify what are the factors of the numerator and the denominator. Now the factors of the denominator are evident, y plus 2 and y minus 2. But the numerator, the factors are not so evident. It might be the case that after we simplify all of this arithmetic out, that there's a factor upstairs that we're not seeing. So this is the one place where we want to multiply everything out and then collect the like terms. So if I do that, upstairs I'm going to get a y plus 2 times y is going to give me y squared plus 2y. And then I'm going to have negative 8 times y and negative 8 times negative 1. So what I'm going to get there is minus 8y, and that'll say plus 8. Here I'm fixing the error that I made earlier as we go along. So what I end up with is y squared plus 2y minus 8y plus 8. And I have this middle term, which is a pair of like terms, plus 2y minus 8y. So how many y's do I end up with there? I end up with minus 6y. And then, again, fixing my error as I go along. This is a plus 8 right here. And so now I've totally simplified what I have in my numerator. My denominator, I can still see what the factors are, but my numerator, I don't know offhand what the factors are. So now is the time for me to factor it. Does y squared minus 6y plus 8 factor in any meaningful way? Because we won't know whether this fraction is in its lowest terms, whether it's been completely simplified, unless we know for sure that there are no mysterious common factors upstairs and downstairs. What do you think about y squared minus 6y plus 8? I think it factors, actually. We'd be looking here for a pair of numbers which multiply together to give me 8. But which also add together to give me negative 6.
Would be plus 4 and plus 2?
Close.
Sorry, negative
Minus 4 and minus 2. There we go. Exactly. Negative 4 and negative 2. Y minus 4, y minus 2. That product of binomials gives me y squared minus 6y plus 8. And so this factoring step, if we hadn't done this, we wouldn't have discovered that, oh, actually, there's a common factor in the numerator and the denominator. What is the common factor?
Y minus 2.
Y minus 2. So our last step in this problem is to divide that common factor away. And our final answer then is that quotient which survives, y minus 4 over y plus 2. And that's the end of the problem. So addition and subtraction problems for rational expressions, they tend to have a lot of work associated with them because take a look at how many times we had to factor. We not only factored at the beginning to try and make our work of finding common denominators go more smoothly, but we also ended up having to factor later on to figure out whether our final answer after we subtract and get a single fraction is written as simply as possible. So there's two places here where factoring is a good idea. And in the middle, there was a place where keeping things factored was actually a bad idea. Right? Here we wanted to multiply out everything which was in the numerator so that we could figure out whether the numerator had anything in common with the denominator that we could cancel. Notice one place that I never multiply things back out is in the denominators. There's never really a reason to turn this back into y squared plus, or y squared minus 4. Because even if I did, later on I would probably have to just factor it back anyway when it came time to simplify. So if you're looking for ways of organizing your work in these kinds of problems, try to avoid multiplying denominators back out. But there are times where multiplying numerators back out is a good idea. Because if we hadn't done that here, we wouldn't have known that there was a secret factor of y minus 2 in this numerator that could be canceled out with a common y minus 2 factor in the denominator.